Welcome back, everybody. Today it is Unit 7, Day 3, dot product. And it is I, Mrs. Fisher. And hopefully today I am going to answer some of your burning questions about vectors, such as, can we determine if two vectors are parallel to each other? If they're perpendicular to each other? Can we apply vectors to 3 dimensions? Yes, friends, all of these burning questions will be answered today with our study of dot product and 3D vectors. It's an exciting day. So, big topic, angles between two vectors. That is going to be able to determine for us whether things are parallel or perpendicular. So, in order to do that, we are going to have to find something called the dot product. All right, so to start off with, let's figure out what the dot product is. I'm not sure who came up with this, who figured this out, but I do know that it is derived from the law of cosines. I am not going to go through that with you because that would make our video really long, but if you are interested in that, you can look up where the dot product comes from. So please just know that it comes from the law of cosines. Even though this says product, this is not multiplying two vectors together. This is going to give us a scalar number, not a vector quantity. Okay, so this is just a scalar. It does not have any kind of direction to it. So the rule for dot product, I'm going to write down that this is a scalar quantity. Okay, the rule is that the dot product between two vectors, so between V and W, so please notice I made a gigantic dot here. That does not mean times, that means dot, as in dot product. So it is a big dot. It's larger than a multiplication sign. So that dot product between two vectors is found by doing x1, x2 plus y1, y2. So the two x components of the two vectors plus the two y components of the two vectors. And that's the rule for finding the dot product. So if we do a little example, let's say vector v has the components 4, -5, and vector w has the components -2, 7. Then I can just simply ask you to find the dot product. So that will look like this. And what you get is this silly number that seems pointless right now, but we will use it later on. But all you do is the two x quantities. So x times x. So 4 times -2. Plus, we are going to do y times y. So -5 times 7. And we get -8 plus -35. And we get -43. So that is our dot product. All right, now that really doesn't serve much of a purpose yet. So right now we might just ask you a bunch of questions like find the dot product. Okay? But then we are going to apply that to actually find the angle between two vectors. And again, this stuff comes from doing the law of cosines. So to find the angle, which will answer your first burning question, how do we find the angle between two vectors? So to find the angle between two vectors, you would use the formula that the cosine of theta, where theta is the angle between two vectors, is found by doing the dot product between the two vectors divided by the magnitude of the first vector times the magnitude of the second vector. Okay, so notice the gigantic dot on top, that's dot product. The small dot at the bottom, that is multiplication. Okay, so we are multiplying the magnitudes at the bottom. We're doing the dot product at the top. So if you actually want to find the angle, you will ultimately have to do the inverse. So here's what the formula is in any kind of textbook. You'll see it written like that. So theta really is going to be the inverse of all of this. You just don't normally see it written like this, but this is basically what you're going to have to do. All right, so... Okay. Okay, so a problem that you'll have would be to find... Pause for a second. Don't look at the screen. Don't look at the cool little graphic behind the curtain. That's for later. So for this example, it'll just say something like find the angle between vector v, which will have components of 2, 3, let's say, and w, negative 2, 5. All right, so to do that, you just substitute everything into the formula. So cosine theta equals, and we need to do the dot product. So dot product is that basic formula, x times x, so 2 times negative 2, and then y times y, so 3 times 5. And then over the magnitudes. Now your magnitudes are going to be the square root of x squared plus y squared. So you are going to have to do, for v, 2 squared plus 3 squared, and for w, negative 2 squared plus 5 squared. Okay, so v is right here, and then w is right here. We're finding the magnitudes there. All right, and then you're going to simplify. So up top we get negative 4 plus 15. In the bottom, so that's 11. And at the bottom we get square root of 13 and square root of 29. So altogether, that's the square root of 377. Yikes. So we end up with cosine of theta equals 11 over the square root of 377. So if we're going to actually find theta, we need to do the inverse cosine of that. And we get from our handy-dandy calculator that theta is 55.5 degrees. Voila. All you're doing is typing into your calculator. Now, in terms of whether or not things are parallel or perpendicular, how would you know if it's going to be perpendicular to each other? The angle is going to be 90. That's right, class. The angle would end up being 90 degrees. Now, I want you to think about that. In your formula, if the angle is going to be 90 degrees, what would happen to your lovely little formula? We have cosine theta equals all this lovely stuff. Whoa. All right, so think about this. Okay. If your angle, again, don't look at this graphic, that's for later. If your angle is 90 degrees, I want you to think and imagine this is 90 degrees right here. What is the cosine of 90 degrees? 0. That's right, class, it's 0. And if that equals 0, and I solve this little equation here, then we multiply the denominator over to here, you would get 0 equals the dot product. So essentially the only way that you have perpendicular vectors is when your dot product equals 0. So let's summarize that. If your dot product equals 0, then the vectors are perpendicular. And the fancy name for that is to say that they are orthogonal. So if you ever see the word orthogonal, like on WebAssign, it just means that they're perpendicular. But this little rule right here, dot product equaling 0, comes up a lot. That is really important. All right. If your vectors are going to be parallel, basically what that means is that the components are going to be multiples of each other, because that means that they're going in the same direction. So we'll write that down. If they're parallel, the components will be multiples of each other. Okay, so as an example, determine if parallel, perpendicular, or neither. Okay, and your vectors are going to be v equals -3, 4, and w equals 20, 15. So the very first thing I would do is I would check and see if these are multiples of each other. So by multiples of each other, I mean, can you multiply -3, 4 by a scalar and get 20 and 15? And so I don't think you can multiply those. An easy way you can check is to take 20 divided by -3 and see if you get the same decimal that you get when you do 15 divided by 4. Since those are not equivalent, you would say, therefore, these are not parallel. They're not in the same ratio. These are not multiples of each other, okay? So the next thing I would check is to see if they are perpendicular to each other. If they're going to be perpendicular or orthogonal, then their dot product should equal 0. So you're going to check the dot product. It's -3 times 20, so x1, x2, plus 4 times 15, so y1, y2, going to equal 0 or not. So this is what we're checking. So this gives us -60 plus 60. So would you look at that? You get 0 equals 0, which means that this is orthogonal. So therefore, perpendicular, or the fancy word, orthogonal. All right, so that brings us to three-dimensional vectors. So I found this little graphic that I wanted to share with you because I cannot draw in 3 dimensions. I don't know if you can draw in 3 dimensions, but I cannot. So this is just a little sample of the 3-dimensional plane. We will not be drawing in 3D, but the 3-dimensional plane essentially just shows right here that you've got X kind of coming out at you, Y going off here to the right, and then Z is going up into the air. And so I just found that graphic, and I was like, oh, that's much better than I can draw it. So I wanted to just show that to you. And then they have drawn a vector on this one in particular. They've got a vector going A to B. So that's a vector in 3D space. So we're going to talk about vectors in 3D, but we're not going to actually draw it because, as you can see, that would be kind of a nightmare to draw. But it looks pretty cool if you've got the computer graphics to do it. So in 3D, we're going to basically do everything the same way that we would normally do vectors in 2 dimensions. So the difference is you're going to add on a third component. So your components now, you're going to have x1, y1, and then z1, because you now have x, y, and z if you were plotting it out. If you were doing it with the i's and j's, your vector is now going to be a number and then I, and then a number and then j, and then a number and then k. So you now have a k component. Other than that, it's pretty much everything's the same. You just have this third component. So, as an example, let's say your initial point is the point A at -4, -5. And I guess 0 here. 0. I'm sorry, I'm trying to use the graph that they have here, and I don't have that problem in front of me, and I want to make it accurate. But I'm having a hard time interpreting what they did. Oh, I see what they did. So it's out to, so erase, out to, left 4, and down 5. So that's following the lines here. Out to, left 4, down 5. That's point A. For those of you wondering how I figured that out. Point B is going out 4 on the X. It's going to the right 5. And it's going up in the air. Lord, I don't know. This many. We'll just take a stab in the dark and say that that's about 4. It's hard to tell in 3D, so this is part of why we don't try to draw in 3D, but that looks like it's about 4. I'm guessing. Okay, so if we are going to find out what the vector A to B is on this lovely picture here, from A to B, what we would do then is use that formula that we developed in class the other day, because we can't really draw and make a triangle and do Pythagorean theorem. So that formula for finding the vector A to B would be to do your x minus x, y minus y, and z minus z. So A to B is going to be x2 minus x1, y2 minus y1, and then z2 minus z1. Okay, so it's the same thing as that formula that we had. It's just now you've got 3 dimensions. All right, so this is going to be 4 minus 2, because point B is your terminal point. So 4 minus 2, 5 minus negative 4, and 4 minus negative 5. And so, according to that, to go from point A to point B, you would go out 2, over 9, up 9, to get from point A to point B. All right, everything else works the same exact way. Again, you're just adding on a dimension. So, dot product. So, if we had vector A and B, oh, sorry, that's not going to work. So, dot product. If we had 2 vectors, V and W, the rule for dot product is going to be x1, x2, plus y1, y2, plus z1, z2. If we're finding an angle between 2 vectors, it's going to be cosine equals dot product over the magnitudes. And you might be saying, Mrs. Fisher, how do we find the magnitudes? Great question. Glad you asked. Magnitudes. So in 3D, if you're trying to find the magnitude, it's going to be a Pythagorean theorem thing. You're going to have x1 squared plus y1 squared plus z1 squared. You just can't really do a picture and do it that way. You're going to have to do the formula. All right, everything is basically the same. So if we do an example, and I give you vector V is 2, 3, negative 2, and W, vector W, is 3, negative 4, 5. I can ask you all kinds of things here. If I just say, what is the magnitude of V? You would just do 2 squared plus 3 squared plus negative 2 squared. And so we would just do 4 plus 9 plus 4. Square root of 17. If I asked you to do dot product, you would do x1, x2, plus y1, y2, plus my goodness, z1 and z2. So negative 2 times 5. And so you'd multiply all those together and you would end up getting negative 16. Okay, if I asked you to do 2v minus w, you would double v, so that would be 4, 6, negative 4, and you would subtract w. So 4 minus 3, 1, 6 minus negative 4, 10, negative 4 minus 5, negative 9. Okay, everything is the same as it is in 2 dimensions. You just add on this third component. All right, I think we're calling it quits on that today. We will do some practice. Okay, have a great day. We'll catch you all on the flip side.